Now we've seen that humans can exert a stress of around 10 to the 5 newtons per square meter. But that's not really the force our muscles are exerting, that's the force we are exerting. There's usually a bit of lever action in the whole system that makes it a bit different. Here, for example, is me trying to lift a physics textbook, very heavy. And what you can see is happening here, we're hinging, my bone runs down here somewhere, and there's another bone out there. And the muscle that's doing the work is in here, it's attached somewhere up the top there, and it's pulling somewhere on the bone like there. This muscle is shrinking and applying an upward force here. And that's enough to lift the book. The book, meanwhile, is applying a downward weight force, mg, over there. Now, is F equal to mg? No, it isn't. Remember, this is a lever. And as you know, with any lever, probably remember all the way from primary school, here's the fulcrum where it's actually hinged. You need to apply very strong force close to the fulcrum to give a much weaker force further away. On the other hand, a small motion here gives a very big motion there, so things actually cancel out in that respect. But nonetheless, it means that the force our muscle needs to exert is going to be a lot more than the actual force we exert with our hand. How can we estimate that? Well, here's our simple physical model. So we have our hinge here. We've got distance here, which is, let's call it L. And then we've got the weight over here, mg. We've got an upward force here. And let's call that, I don't know, capital L. Now for my body, this distance, which is from the bone joint to the where the muscle's attached, is going to be about 3 centimeters. And the total length here is about 30 centimeters. Now the way you calculate things like this is using what are called torques. Now a torque in this situation is just the force times the distance. So torque, written with the Greek letter tau, is equal to force times distance, where the distance is the distance from the hinge. Now, there are some technicalities. These all have to be at right angles, which they are close enough in the situation. If it's at some funny angle, it's a bit different. But that'll do for the moment. Now, when you're lifting something at a steady pace, the torques will balance. So the downward torque, to be precise, the clockwise torque caused by the weight of the textbook, or whatever I'm carrying, must balance the anti-clockwise torque caused by the muscles. So the total torque equals F times L plus mg times big L. And that must be 0 if it's rotating at a constant speed. If it's accelerating, jerking it upwards, then the net torque would be in the anti-clockwise direction. But if I just lift the weight at a steady pace, they balance. So what that tells us is that the weight force my muscles are exerting is equal to mass G times L over L. So it's the mass I can lift times G times, in this case, 30 centimeters over 3 centimeters, so it's about 10 times that. Now I know from the ANU gym that the maximum weight I can lift in this position is roughly 6 kilograms. So that tells me the force is going to be roughly 6 times 10 times 10. So it's about 600 newtons. That's the force. What's the stress? It's going to be the force divided by the cross-sectional area. And the cross-sectional area is roughly 5 centimeters times 5 centimeters for my bicep muscles. They're smaller than my thigh muscles. So stress is going to be about 600 over 0.05 squared, which comes out as about 2 by 10 to the 5 newtons per meter squared. And that actually turns out to be a good generic figure for the strength of muscles across the entire animal kingdom, whether it's hummingbird wings or grasshopper legs or mouse muscles or elite athletes. They all have about the same stress, all about 2 by 10 to the 5 newtons per meter squared. Some are stronger than others, but that's usually because their muscles are thicker. There are, of course, many complications to this about fast twitch and slow twitch, but for ninja purposes, that's actually a remarkably uniform number. And the question is, why is the number this? Why hasn't any creatures evolved muscles that are, say, 2 by 10 to the 6 or 10 to the 7, in which case they would have much greater strength from much smaller muscles? Is there some fundamental reason why we can't do better than this?